Before we talk more about the normal distribution in particular, just a quick reminder on those functions that we talked about at the end of chapter 4, where here we're looking at what are called probability density functions, or PDFs. We talk about these as distribution functions and cumulative distribution functions. Here we're specifically looking at density because we have a density of options when we're talking about things that are continuous rather than discrete. So I talked about a bit in that last video that when we're thinking of this function, we're thinking of a smooth, continuous curve that describes all of our potential values in terms of our distribution. Thinking of that like the frequency polygon for infinitely thin classes, where with this, we essentially always have to bear in mind that continuous means any possibility has to be considered here. Anything that we can possibly think of as being within our distribution is a potential value for our distribution. It takes infinitely many options. So to understand this, let's think about discrete things one last time. So let's say you've got some selection of options, and I'll say it's 0, 1, 2, 3, or 4. I don't know what those 4 things are. Let's say they're gold bricks. I don't know. But if you want to talk about them as discrete objects, you have none of them, 1 of them, 2, 3, or 4 of them. Those are the only 5 things that can possibly happen. And if you want to talk about this in terms of having, say, less than 2 in this setup, that means you have either 0 or 1. If you're talking about more than 2, that means you'd have 3 or 4. And if you wanted to talk about some value in between, a window from 1 to 3, you'd have 1, 2, or 3. You just have those discrete options where the gap from 1 to 2 or 2 to 3 might as well not exist. Or you could also think that it might as well be infinitely wide because there's no possible way to connect them. You can't really talk about it in terms of what goes on in the middle there. But if we change our frame of reference and talk about things in terms of continuous values, and we want to talk about things less than 2, well, we definitely have 0 and 1, but we also have things like 1/2 somewhere in the middle, 1.5, then 1.25, 1.1, 1.01, 1.001, and so on down the line, getting closer and closer to 1. But we can also get very, very close to 2. And you go 2 3/4, 2.9, 2.99, 2.999, 2.99999999999999999999999999999, and we're still nowhere near close to describing all of our options. We're still nowhere near close to getting as close as we'll really end up being. Because when we have continuous things, anything less than 2 is anything less than 2. Or in some sense, everything less than 2. And the thing about infinity is that the human mind's not really designed to comprehend it very well, because think of any number as close as you possibly want to 2. And you're still going to have some infinitely small amount of difference in there that has infinitely many values that are still not described. It's kind of weird. It's a bit hard to really grasp mentally, but the main thing you should take away from this is an understanding of the idea that when we're looking at continuous things, and we're looking at continuous things whenever we're talking about the normal distribution, we are talking in terms of this kind of infinite level of description. So one thing that's important to note here, when you're talking about that, is if you want less than 2, we're technically not including 2, but really, we're getting so very close to 2 that the difference between less than 2, so if we say x, actually I use the red one because that one's got a little bit more life to it. x is less than 2, and we want to talk about that in terms of a probability of some kind, it's not really all that different from saying x is at most 2, at least in this context, because the 2 itself doesn't mean a whole lot compared to the infinitely many things that get very close to it, and the infinitely small gap from whatever gets as close as we want to 2 itself. Of course, with all those values, there's so many of them, and some of them are so small in difference that we really don't care about most of them. But it's important to know that they are there and that we are counting them. However, because that specificity leaves so many options, in terms of probabilities, we don't get a whole lot from points. So the PDF is a useful function. The probability density function is not worthless, but for what we're doing here, when we're trying to describe probabilities in terms of not simple events, or even in terms of simple events, really, for this, we don't have a whole lot of meaning ascribed to the probability of a single value, because a single value is so impossibly small and rare that it's not really worth considering in that context, at least not for where we are. So generally, we do all of our work here with the CDFs, and we'll see what that looks like more when we get into some examples here, but just understand that the PDF is nice, we just don't use it very much for this. It's not really what we're looking for. But hopefully, we now have maybe not a cleaner picture of how these continuous distributions work, but then we have a little bit more of an understanding of what it means to be continuous versus being discrete. And I'll say that with this stuff as well, it'll come up more when we get to applied examples, but we're going to have to make some assumptions to fit these models that aren't quite realistic. We'll see that when we get there, but so there's a little bit of smoothing going on here that maybe isn't fair. Anyway, the next thing we're going to talk about here is what these distributions, specifically normal distributions, look like in terms of the 2 most important measures that they're built around, the mean and the standard deviation. When it comes to normal distribution, all of our discussion is built around those 2 parameters, mu and sigma. So it's very important that we have some understanding of what they look like for our distribution in general.